So last video, we learned how mu1 minus mu2 problems, difference of two means, works for confidence intervals. This video, we're going to take that same concept of subtracting two means and do it to our HOHA significance tests. So the first thing we want to do when we're setting up one of these problems is set up our hypotheses. And just like with P problems, there are going to be two ways you can choose to go about it. You could just say for your null that the means are the same, and then your HA would be either mu1 is less than, greater than, or not equal to mu2. And you could do it this way. Makes logical sense. For the sake of our calculations, though, it is often easier to use the zero that we're used to seeing. So we would instead say the equivalent mu1 minus mu2 equals 0. And then your HA would be that it's greater than, it's less than, or it's not equal to 0. Either method is acceptable. This is a little easier, in my opinion, even though it looks less nice, because you get to think of that idea of, okay, am I going to get a positive result or a negative result, and what does that mean for my test statistic? So actually calculating a test statistic, remember for mean problems, we do use a t-test statistic here. And the way that that goes is it sets up with statistic minus parameter, or value minus mean for the top. So we would be looking here. My statistic is what I get from my sample. That's going to be x1 bar minus x2 bar. That's my sample results. Minus, I would put my mean over here, which is going to be mu1 minus mu2 for this next part. But when we set up a significance test, we almost always assume that the difference in the two means for our null hypothesis is 0. So I actually can make this one easier on myself by putting a 0 there. It should say mu1 minus mu2, but you go into a significance test assuming the difference is 0. So I can save myself a little effort right there. And that's going to get put over the standard deviation. And you will recall the formula for that is that S1 squared over N1 plus S2 squared over N2 that we would have seen back on the last page when we were doing our little setup right here. So we're using the S version of that formula. In the last section with P, there was a little bit of weirdness with that whole combined proportion that basically we were forced to do a weird, confusing step since we didn't have access to the individual proportions themselves. That doesn't come into play here. This is honestly a little easier than the P version of the formula. And again, we're going through conditions. We've got either random sample, I should say independent random samples, or you could say that you have random assignment to treatments. You've got your two 10% conditions. I wrote it out last time. I'm not going to do it again. One thing I forgot to mention in the last video, you only need to use the 10% condition if you are sampling without replacements. If you're doing an experiment where you're just like randomly assigning to treatments, you actually don't have to worry about the 10% condition. So it's only when you're sampling that you need to address the 10%. And then we've got our last condition, which can either be the 30 check, central limit theorem, or the normal population, or graph your data. You've seen this lots of times now, so it should be starting to become familiar to you all. So those are our conditions here. And I mentioned calculator commands last time, but let me pull up that menu and show you guys what you're using in this section, since we have this box still blank here. So we use t-test for one sample problems. This is a two sample or two mean setup right here. You will either want number 4, two sample t-test, or you will want 0, two sample t-interval. And those are going to be our two choices. So that was going to be number 4, two sample t-tests, or number 0 to sample t interval. And then you just choose the appropriate option. So degrees of freedom are going to work exactly like before. Again, technology allows us to get a better degrees of freedom that sort of blends our two sample sizes and gets us some sort of like mysterious degrees of freedom that's usually a decimal. Whereas if you were forced to do it by hand, you probably wouldn't use the formula. You would just default to the smaller of your two group sizes. But we're going to use technology whenever possible. And then our problem for this video is going to be as follows. These two girls want to see whether helium balloons deflate faster than balloons that you just fill with air. And they wanted to look at how quickly those balloons are going to deflate. So they've got 60 balloons. They made sure those balloons were all the same type. So it's not like they have like the stretchy balloons and then those like foily, I don't know which they're called, the birthday balloons with like the almost aluminum foil. That's all the same, whatever they chose to do there. I'm picturing just your traditional birthday stretchy balloons. And they decided to take those 60 balloons that they purchased and randomly divide them into two sets of 30. One set gets helium, one set gets air, and they're going to look at the circumference around the balloons immediately and 3 days later. And they're going to compare how much. If you look at what they actually measured right here, they're not measuring the size of the balloons. They are measuring how much the balloons decrease by. So that'll come into play when we actually go about setting up our significance test. My first question for you guys, though, is sort of a review question way back from chapter 4 at the very beginning of the year. Why was it important that they use the same type of balloon for everything and they didn't mix up like the stretchy balloons with the foily balloons and like all the different kinds? So why is that an issue? So if you're thinking about that, kind of come up with your own answer. Why couldn't they mix up the types of balloons? The answer to that is because the different types of balloons may respond differently or deflate at different rates. You've got more variability in your data if you mix up balloon types. It's better just to stick with one so you have less variability. That's the concept of control in an experiment. So if I flip ahead here to the yeah, that's pretty much exactly verbatim what I just said there. Control is when you keep all those other variables that you're not testing consistent. That way you can really focus in on the thing you're trying to measure, which is helium versus air. So they ask us in this problem to set up a significance test to see if helium balloons deflate faster than air-filled balloons. So our first move is going to end up being to define our variables. You can choose subscripts with letters or with numbers. I went helium and air. But the little distinction you got to make when you're doing this problem here, we are looking not at how much air is left in the balloons or how much helium is left. We're looking, if you look at the measurements up here, at how much they decreased by. So we're choosing to measure the decrease rather than the actual amount left. So when I define my variables, mu sub h is the true mean decrease in circumference for the helium, and then mu sub a would be the same thing, but for the air balloons. And I made sure I defined my alpha. They don't specify, so I just use good old 0.05. And if you look at my hypotheses here, null hypothesis, there's no difference. The balloons deflate at the same rates. But for my alternative, I chose to go H minus A in that direction, and that's my choice as long as I specify what I'm doing here. But if I think helium is going to deflate faster, that means the decrease for H is going to be bigger than the decrease for A, so I used a greater than 0. If I instead define my variable to be how much air is left, well, then I would think H is going to be smaller or less than A. It's all about what you're measuring in the problem. So we set this up. We suspected helium deflates faster, so the decrease will be greater for that. So checking my conditions here, we did not sample these balloons. They didn't promise they went to the store and like pulled random balloons. They bought a bag, presumably. But what they did is they randomly assigned 30 of those balloons to each treatment group. So we had random assignment here, which covers independence in random assignment. We did not have random sampling. That would affect our scope of inference on this problem. So like if I was talking about where can I apply my results, I would have to say just balloons like the ones that I bought, not necessarily all the other packs of balloons in the store. Maybe a different pack of the same kind of balloons are stretchier or less stretchy or whatever. Because I didn't sample from the population, I don't have to worry about the 10% condition. I straight up said here the 10% condition is not needed. You could choose just to not address it altogether. You don't have to say, oh, I don't need to do this. You can just not do it when it's relevant to say so. And then luckily, our sample sizes are both at least 30. So we can go ahead and do our t-test on this problem. So when you actually type this in the calculator, this time I am running a test, not just an interval. So I would want number 4 here. We did the data tab last time on the cookie problem because they gave us the raw numbers. Here they summarized for us what is going on with the decrease. So I'm going to choose the stats tab, and then I can just fill in the info from the problem. My first parameter is the helium. That had a decrease of 26.5 and a standard deviation of 1.92. There were 30 of those. And in my second group, I had a 2.1 and a 2.79 standard deviation, also sample size 30. My alternative is a greater than sign if you look at what I wrote down below. So I choose the greater than sign option here. And again, we always say no to pooling on mean problems. If I calculate that, it's going to spit out info that you see written down right here. Now, if you look at what's going on here, my test statistic was almost 40. That is ridiculously high. We usually get like 1 point something, 2 point something. But look at what happened in our data. We had a mean difference of 26 centimeters for the helium group versus 2 centimeters for the air group. It's pretty obvious that is a big difference right there. That difference, that ginormous, almost like it's not due to chance. It's just not. And if you look at the p-value, I have to move my decimal 40 places over. It's basically 0. It is so unlikely that those results just occurred due to chance. It pretty convincingly tells us, hey, the helium does deflate faster. That's what's going on right there. And if you look at the degrees of freedom, I had a group of 30 and 30. It's not quite 60 degrees of freedom, or 59, but it is better than just the 29 we would get from the conservative model. So it somehow blends it together and gives us an option here that just spits out at us. So I would choose on this problem to write down the name of the test statistic, p-value, which was basically 0, and my degrees of freedom. All of those things are important, and you have to get them down in your paper there. Then we just do our regular conclusion. So because our p-value is so low, it's definitely less than our alpha, we're going to reject HO. We're rejecting the idea that the average amount of decrease is the same. Pretty clearly, there's convincing evidence that the helium balloons do deflate faster. I chose to say the mean deflation is greater than that of the air-filled balloons. Factual statements, totally fine for full credit. But what that's really saying is that the helium balloons deflate faster on average. And the last thing I asked you to do there is just interpret our p-value. And that was a script we learned back in chapter 9. So assuming HO is true. So assuming that the two types of balloons deflate on average at the same rates, the probability of getting a difference between 26 and 2, that large, is basically 0. The probability of that being just due to chance. So just a nice little review of p-value to finish off the lesson there. So these 4-step type problems here with two parameters aren't really that bad. They're a little more complicated looking. There's more to write down, but they follow the same procedures we learned in chapters 7, 8, and 9.